Okay, let's get started. So here's where we left off last time. So just bookkeeping here. You've got, is it written homework due tonight at 5 or midnight? Or online homework? Online is due 5 p.m. today. Online. It's due 5 p.m. today. That's on surface area and arc length. And then you have also a written homework due Wednesday before class, right? You have to upload it before class, 9 a.m. Wednesday. So, so Derek's wife had a baby yesterday. So he will not be with us for the next day or two. So his office hours are canceled, Derek's office hours, but the rest of us have office hours, myself and Pollock. You may have a sub for recitation. Maybe. He might be back. We don't know yet. But so yeah, healthy baby girl. Everyone's good. So where was I going with that? Forgot. Okay, so getting back to this. So this is from Friday. We had the acceleration graphs of these two cars. And the question we asked was, when will the speed of car 2 reach the speed of car 1 for the first time? And we were looking at these as the rate functions for speed. And by thinking about, little changes in little accumulations and accumulation of changes in speed based on these two, we thought maybe somewhere around 5 or 6 was the first time that car 2's speed would catch up to car 1, and then what did we do? We found the functions for the speed, and we graphed those functions to figure out exactly when. And so I can somewhere right around in here, right around 5.6. So our prediction was pretty good, right around 5.6. The speed of car 2 reached that of car 1. And so how did we graph these functions? So let's just review that. I have the acceleration functions. How did we make the graphs of these functions? So can you write down in your notes what you would type into GC to define and graph these functions? So just as a review, where do the speed functions come from? So any volunteer? How am I going to get... So these are the acceleration functions. We have those defined. And this is, say, velocity for car 1, and velocity for car 2. So how do I write the velocity function for car 1? James knows. Raymond, was that almost a hand? That was James. Tia.
The integral.
Integral?
We're just using x instead of a, so it would be from 0 to x.
0 to x. This is what she wants for the speed function for car 1. Is it correct? And it's correct because what is the acceleration of car 1? What is that? The rate of change of speed, right? The acceleration is rate of change of speed. It's how much the speed changes given any change in time. You can calculate how much the speed changes by multiplying the rate times, and that's acceleration, times a little change in time, and that gives you the corresponding change in speed. So if this is the rate function, we know this is our net accumulation function. So net accumulation of changes in velocity, those changes accumulating to give us the current velocity, right? And so look, what a powerful thing. For any given time, this function tells us what the speed of the car is. Anywhere from 0 to, in this case, around 8 seconds, 8 or 9 seconds. It gives us the whole profile of speeds, right? So your whole calculus career has been about Functions, building and using functions to model the real world. It gives you all this information. It gives you every single speed for every single time. See, that's a really powerful thing, a function. Okay, and then a graph is a visual representation of that, right? A graph is a visual representation of all that information. You pick any point on here. So here's the point, 6.9375 and 16.9128. And what is that telling us? $16.913. What is that revealing to us about this situation? Somebody knew. I know these guys in front know. So what does that reveal about the situation? Is it Andrew? Tell me your name again in the gray shirt. Joey? Tell me, what does that reveal about the situation? Oh. Okay, don't forget your glasses, or maybe you need to sit closer to right. What's your name? Yeah. Camille?
Yeah.
What does that reveal about the situation? Okay? Yeah, tell me your name.
Joe?
Joe.
Is it at 6.9 seconds to travel at the velocity of 16?
Right. Yeah, so this is the speed function for car 1. So at 6.9375 seconds, the car is going 16.913, I think we said feet per second or something, or whatever the speed units are. Okay? So now I want to know and that's kind of review last time. I want to know, so is this where car 2 passes car 1? Car 2's behind, and then it passes, and now car 2's ahead? No, what did we say? This is when the speed catches up, right? So this is when car 2's speed, but car 1 has been traveling at a higher speed this whole time. So at this point, who is ahead? Car 1's way ahead, right? It's been traveling at a higher speed that whole time. So car 2 is still far behind. So, but then what happens after that? What about the speed comparison now? For x greater than the 5.6 seconds. Now, car 2 is going faster, right? Because you can see, because the coordinates of these points are higher than the coordinates of these points. So the question is, by the end of this time, which is, I think we're talking about, is it 8 seconds? Yeah. At 8 seconds, has car 2 caught up to car 1? By 8 seconds, did car 2 catch up and pass car 1 yet? Yes or no? No. Definitively no? You just know for sure? I want to know for sure. But we're mathematicians. We're in Calc 2. We're smart. How can I figure out for sure if if car 2 has passed car 1 or not? I want to know for sure. We've got all the tools. We've got all the experience. Arc length. So is this the road? Is this the car traveling along the road? No, right? These are speeds, and this is time. This has nothing to do with the paths of the car. So arc length doesn't have anything to do with this, right? Because these are speeds. Y coordinates are speeds. X coordinates are time. So the arc length of this is nothing to do with the car and the situation with the car traveling. All right, so I want to know for sure if car 2 is further in distance than car 1 by 8 seconds. Is that a hand right there? No? Yeah. To get what? Position. If I want to write a position function or distance function, called S1, how would I write that? So what would I need to write the accumulation of distance? Rate of change of distance. If I want to write a net accumulation function, I need the rate of change. So what is the rate of change of distance? Yeah, this one, right? So I could do the integral from 0 to x of v1 of this will give me exactly now. So theoretically, it will give me exactly every distance accumulated by car 1 for any given time, right? Another powerful thing here that's telling me I can choose any time that I want, 2 seconds, 3.6 seconds, 7.2 seconds, and then this function will give me the accumulated distance. Functions are super powerful, and they're what calculus is all about, modeling the real world with functions. Okay? So now how am I going to figure out if car 2 is further than car 1 at 8 seconds? What else do I need to do? Yeah, James.
You have to find the exact rate of change function of the velocity of both cars. Find the function of both cars' velocity.
Okay. So he's saying, so where am I going to get the exact rate of change of velocity? Where am I going to get the exact rate of change of velocity? Well, this is it, right? We did that. Yeah. Okay.
You'd have to evaluate both intervals of both cars from 0 to 8.
Okay, so find S1 of 8 and so yeah, figure out what the distance accumulated for both cars is at 8 seconds. Okay? So let's do that. So let's see here. I have already set that up. So here is, those the acceleration. Here's our speed functions, right? Can you read that in the back? There's the speed functions, and then I need what? And now I need the distance functions. And I can get those distance functions by using the speed as the exact rate of change, right? Exact rate of change of distance is speed. Okay, and then what should I do to find out? So she's suggesting figure out what the distance traveled by the car is at 8 seconds. How can I do that? How can I find the distance traveled by the car at 8 seconds? Yes, sir. Okay, I could graph it. This one, yep, I could graph it. And what else could I do? He wants S1, 0, 8. Will that do it? Yeah, right. So function notation gives us values of the dependent variable. The dependent variable here is distance. So I could do S1 of 0, 8. I could do S2 of 0, 8 and compare those two. Okay, but now I want to graph it because I want to show you something really important from last class. So watch what happens when I graph this out. So here I'm graphing the distance functions, accumulated distance, S1 and S2. Okay, now watch what happens when I graph these. What's going on here that's different than usual? It's taking a really long time, okay? And so I'm gonna leave you in suspense here. I'm not gonna show you if yet. We're talking about something else yet. So we still don't know if at 8 seconds the car 2 has caught up or not. But why did it take so long to graph? Why did it? This is a really important point from last time. Oren. Yeah, so to compute the accumulated distance, that was based on what? Rate of change of speed. But our rate of change of speed was given in what kind of form? Remember what this is called? Open form. Remember open versus closed form? So we're graphing an open form expression whose rate of change is another open form expression. And what do we say about open form expressions? What? Besides the fact that they reflect the meaning and the process behind what's going on, there's something else about open form expressions. What was that? Yeah. Yeah, so it requires technology to compute them. They're not efficient in computing values of the dependent variable. So why is this taking so slow? Why is it taking so long to graph this? Do you see the connection? Open form expressions are not efficient in computing results. And now I'm graphing a net accumulation function that's 2 layers of open form. 2 layers of inefficiency. And even technology is having difficulty with that. So, technology usually does these hard computations for us instantly, but with this 2 layers down of open form, that the net accumulation of distance is an open form based on the rate of change of speed, which is an open form. So it takes it a long time to do that. Okay, now I have those same functions in closed form. So here are those functions in closed form, right? Just basic arithmetic, sine functions, exponents, addition, subtraction, right? That's a little complicated, but that's not a big deal, right? Now watch, and then I have those set up to graph also in this GC window. So watch this. Don't blink. Ready? Don't blink. Watch. This is graphing those distance accumulation functions in closed form. Ready? Did you see it? Did you blink? Do it again. Watch. Graph. Boom. Done. Why so fast? Closed form is efficient, and our GC loves it, right? It's just, I can do that super fast. Because in closed form, computations occur very efficiently. So does car 2 catch up? It still doesn't catch up to car 1 at 8 seconds. Just barely, right? So the y coordinate of that point would be the distance, the accumulated distance of car 2, and the y coordinate of that point would be the accumulated distance of car 1. Car 2 still didn't catch up. Okay, questions on this? So we got lots of important concepts going on here. The rate of change of accumulated distance is speed. The rate of change of accumulated changes in speed is acceleration. That's an important concept here. And then the difference between this, when we graph these, it's demonstrating the difference in efficiency of open form versus closed form. Even GC has a rough time when you have 2 layers of open form that it has to graph versus closed form. Okay, any questions on our distance, speed, acceleration? Does all that make sense? Okay, let's change the subject here. Another quantity we're talking about next. We're getting into physics stuff here. We want to talk about work. So we haven't done work yet in this class. Did you know that? Get it? We're going to do work for the first time today. I got jokes. All right, so work, is, if you learned your physics, is a force applied over a distance. A force applied over distance is work. So for me to push this chair across the floor, I have to do work, right? That makes sense. I'm doing work to do that. Okay? So the quantification of that, the basic simple formula is force times distance. That's how we get work, force times distance. But as we'll see in a second, there are things that complicate that, all right? So it gets more complicated. But the basis for work is force times distance. All right, so what about our friend here at the Midvale School for the Gifted? How much work is he doing? He could push with tremendous force, thousands of pounds of force on that door. That's a pull door. And how much work does he do? 0, okay? It's 0 because work is about force applied over a distance, actually creating a change in the position of something. Okay? So this young man is doing no work on that door. Okay? So we can think about, so have I done any work on the chair yet? Okay, now how about now? Yep. And what about now compared to before? What's happening to the amount of work I'm doing? Isn't it increasing as I increase in distance, right? So what is that theme? This is this theme we've been talking about all semester, right? That as I push, the amount of work I do does what? Accumulates, right? So it's accumulated or accomplished work at any given distance that I've traveled. My work is continually accumulating. All right, so like I said, there's complications to this. It's not, so if I push with a constant force for a certain distance, I can calculate the amount of work just by doing force times distance, but there's complications to this. So the force varies. Force varies as we're applying it through the distance, or the distance varies in odd ways, right? So this complicates it, and we can't just plug in a force, plug in a distance, and multiply and be done. Okay, so we got this situation here called the pushy ant. So the ant is pushing a seed. Along this path, and the ant uses a constant force of 0.03 newtons. How much work will the ant have accomplished at each distance along the path? Okay, so why can't I just use a straight up force times distance? What's the problem here that I can't just say force times distance equals work? Yeah, so like when the ant gets here, what's the kind of the unknown thing here? Yeah, what is this crazy curved, squiggly distance, right? What is the squiggly distance? Okay, so what we need to do then is think about a little bit of work at a time, right? So that's the idea of accumulation. Work is going to accumulate bit by bit, and so I want to think about a little bit of work. So we know that work is force times distance. If I just wanted to say the little bit of work of the ant, say right around that little bend right there, how could I calculate that little bit of work, say right for a little, like 2 steps that the ant takes around that bend? So what would it be? So it's work is still force times distance. So in that scenario, what is the force and what is the distance? Say for a little teeny part of the path. Is that almost a hand? No, okay. Yeah, Sarah.
It'd be force times ds.
Force times, so force. And what is the force the ant is pushing with? And that stays the same. That's nice, right? So we can use the 0.03. So yes, it's going to be force. And so then what's the distance? She said ds. Is that right? A little bit of distance along the curve. Is that ds? Yeah, that's our arc length, right? So arc length has everything to do with this now because distance along a path, that's arc length. So force times ds. Excellent. And so then what is the force? It stays constant. We like that. And then what is ds? What is ds? Who remembers? Square root. I heard some square roots. Good. Square root of? Yeah, so if this was function, say if this is function f, it'd be the derivative of the function that squared. Is that it? dx, right? So ds includes dx. Right? This is the rate of change. That's the rate of change of our arc length. But if we want ds, then we need the little variation in arc length is the rate times the little variation in x. So right, so So what is the rate of change of work? Coming back to this, if dW equals force times ds, what's the rate of change of work along the path? Does that look familiar? dW equals something times ds. Rate of change would be then? Force, right? This is like dy equals mdx, right? So this is like our little change in dependent equals something times a little change in independent. Therefore, rate of change is rate of change of work is force. Just like rate of change of speed was acceleration and rate of change of distance traveled was speed. Rate of change of work is force. And so the rate of change of work with respect to x, then we can do the same thing. Now, basically what this square root function does, it's like a transformation from the s quantity along the path to x, horizontal distance traveled, right? So that square root does a transformation for us, taking us from, the quantity along the curve to making the independent quantity horizontal distance x. So then our rate of change function is all this in terms of x. So r sub w of x is force times that, which is still force. It's just force, rate of change of force with respect to the horizontal quantity x rather than with respect to along the arc length, ds. Does that make sense? So this is also dy equals m dx. So the m is this whole thing. It's the force along the path converted to force in the horizontal direction by the square root. Does that make sense? Okay, so let's put this in GC and see what we get here. So yeah, I kind of jumped the gun here. So this is all based on this function being some function that we can model in xy plane. And so here's that function, x plus 0.3, etc. So I have that started here. Okay, so now I want to create the work function for the ant. And I want that work function in terms of how much horizontal distance the ant has covered as it's doing this crazy squiggle path. Okay? So how will I do that? What should I type in GC to come up with this? Eventually I want the work, and we're going to call this work 1, because we're going to do another one later. So work 1, and I want to use my 2-argument function notation. So this is going to be the work accomplished by the ant as a function of how much horizontal position the ant has made. So what am I going to need to do to get this function? And I'm going to graph that. We're going to take a look at that. What do I need to do to set that up? Somebody new? Yes, sir. Okay. All right, so he's offering up. We're going to do the force, and then this is our what? Converting from along the arc length to x. So that whole thing is our rate of change of work with respect to x. So I'm going to use the total derivative here of f. And you wanted to use t's. So as I'm typing this in, see if you agree with him. Do you agree with this? Do you agree with that? Does that get the work done, the accumulated work done by the ant as a function of horizontal distance covered by the ant? Yes? There's one nod. Yeah, got a couple thumbs up, Okay. So we could have also set up, if we wanted to, as an intermediate step, what could we have also done?
You could just define the derivative before it and insert it in that.
Okay, that's one thing we could have done. We could have defined the derivative here and then inserted there. What else could we have done? Similar kind of thing. Yeah, Adam. Okay. So what about the whole? So yeah, you guys are both getting at it. So what about the whole rate function? We could have defined the whole rate function. Sometimes that's really helpful when these rate function gets complicated. To define the rate function, so the 0.03 times this, and then when you set up the accumulation function, all you need to do is use the function notation, r sub wt. But this is perfectly fine. So let's graph this. How do I graph this? So I want to graph this. Y equals. I want to assign to the y-axis. What do I want to assign to the y-axis? Capital F, little f, capital W. I want to put the work on the y-axis. And when I want to start at what? When I graph it, I want to start at 0. And what do I want to put on the x-axis? I want to put x, right? I want to put x on the x-axis. So I'm just going to leave it as x. And we can graph that from 0 to, it looks like maybe 3.5. Does it look like we have everything right? Okay, I'm going to graph it. And so what do we expect? Let's think about what are we going to expect for what the graph looks like. So where's it going to start? At x equals 0, what will the y-coordinate be? 0.3? So at 0, when I graph this function right here, what will I get? How much accumulated work has there been? 0. It's going to start at 0. And what's it going to do? Is it going to kind of take a path like this? Accumulated work? What's that? Straight up. Will it always increase? Will the work ever decrease? As the ant is pushing along this curve, will the accumulated work ever go down? It will never go down, right? Because the ant is always, the accomplished work by the ant is always increasing. It doesn't know that it's pushing it in the negative y direction or the positive y direction. That doesn't matter. The ant is always adding to the work that it's doing, no matter what direction in this graph that it's pushing. Right? It could push back, it could push to the left, to the right, up, down. It's still gonna, as long as it's keeps pushing forward, which it will, that accumulated work will always increase. Will it increase straight? Up like this? So when will it have a higher rate of increased work versus a lower rate of increased work? Yeah. Yeah, right. So here right around like this part here, For a change in x, do you see it's going to do a lot more work through there for changes in x than, say, right around 0.5? So for changes in x, it's covering a lot more territory. So we're going to expect around like 0.1, 0.2, 0.3. We're going to see a higher increase in accumulated work than we do at, like, say, 0.5 for a change in x. Does that make sense? Let's take a look. So what did we say? I'll do it again. Around 0.1, 0.2, 0.3. Look, higher increase of work because for a change in x, it's covering a lot more territory, right, up and down, versus at 0.5. When for a change in x, it's covering a lot less ground. See that? And so then we see less increase in accumulated work around 0.5 than we did at 0.1 or 0.2. Okay, so I'm going to pick a point on the graph. $2.119, comma, 0.816, or 186. Okay, I want you to interpret that point on this graph, right? So this is our accumulated work of the ant, the pushy ant. What? Everyone's talking to somebody. You are explaining what the meanings of those numbers are in this context. Go. Tell me. So be specific about, is this the distance that the ant has walked, 2.119? You said distance units. So what's that? X units. Okay, is the 2.119 how far the ant has walked? Yes or no? Is the 2.119 how far the ant has walked at this point? How far he pushed. That's what I mean. How far he pushed. Is that right? Everyone says yes? Adam. Is the 2.119 arc length? Well, so that'd be the same thing, right? The distance that the ant has walked on the arc length would be the same thing. Is that what the 2.119 is? Right, we made this big deal about how we transferred from arc length to what? X, horizontal distance, right? So the 2.119 is not how far, the 2.119 is not how far the ant has walked. Instead, it is, as the ant has walked, how much horizontal distance has it covered? 2.119. So has it walked farther or less than 2.119, say, what is this, I don't know, inches? Has it walked, but when x is 2.119, has it walked farther or not as far as 2.119 inches? Farther, right? It's walked this whole curve. How can we figure out exactly how far it's walked when x reaches 2.119? Yeah. Into this one? So this function tells us, so this y value here is how far the ant has walked. You agree with that? So this is truly the path of the ant. You're looking down on the path of the ant. Is this y coordinate how far the ant has walked? That's less too, right? So I want to know at 2.119 for x, I want to know how far has the ant walked? Yeah? Yeah, that's the arc length function, right? We did right. So that's arc length. So if I want to know how far it's gone at 2.119, I'm going to do arc length. How do I do that? I haven't done that in this file yet. What should I type? I want to do arc length now. So, what do we usually call that? S sub 1 of a to x integral from a to x, right? Let's take a look. See, we never did that. We went right from the path and the force to the work function. We never found an arc length function. I mean, it was kind of in there. But if I want a true arc length function, then what do I put in here? Square root 1 plus. That's this thing, right? I'm just going to copy and paste that. And now how do I find out how far the ant has actually walked along the path when x reaches 2.119 inches? What should I do? Function notation, right? Let GC do the work. I can write S what? S sub 1 of 0, comma 2.119. How far has the ant walked at 2.11 when x, its horizontal position, reaches 2.119? 6.8932 along the arc. That's the arc length function, right? Okay, so now, again, let's go back to, so we're all doing this right now. And 1 through 2, where is it? The 2.119. Find it again. There it is right there. So now, again, interpret this point on the work graph. What exactly is that 2.119 comma 0.186? Because you all told me that 2.119 was how far the ant had pushed along the arc. So instead, what is the meaning of this point? Somebody knew. Yeah, Oren.
So after 2.119 inches of horizontal distance, work accumulated has been 0.186 newton.
Good. So when the ant has covered 2.119 of horizontal change, horizontal distance, which includes all this up and down squiggle like this, or 6.189 of actual distance traveled, gets to 2.119 horizontally, x, then his accomplished work along the path was 0.186. Does it make sense? So this whole thing of, in the work function, the square root thing, that whole thing takes us from, it's a transformation from distance traveled as the independent quantity to just strictly the horizontal distance as the independent quantity. That's what this is like a transformation from that quantity of arc length to the quantity of, as a function of x, purely horizontal distance covered. Okay, so now I got a harder scenario. Any questions about all that? Is this making sense? All right, next scenario. No, not that. So here now the force is 0.03 times s plus 1. Or in other words, as the ant pushes, for whatever reason, the force that the ant's pushing with is increasing as a function of how far it's pushed. Right? Maybe it's collecting dust or something. The seed is collecting some little debris on it, and so it's constantly requiring more and more force that the ant is pushing with. So now, and it's along the same path, So now I want to come up with a work function for this scenario. How am I going to do this? Notice the force. What do I have? I have force as a function of s. So my F2 is a function of s. And it's equal to 0.03 times s plus 1. So this time, let's actually come up with a rate function, okay? I want the rate of change of work and that for our second scenario. So rate of change of work 2 as a function of, I want a function of x. I want my rate of change to be a function of x. How am I going to do this? How am I going to get rate of change? What did we say the rate of change was? Rate of change of work is force. Okay? So can I just do F2 of x? No, because this is expecting arc length along the path. So what can I do so that I'm truly getting the right force function that I need? F2 of what? What's that? Yeah, do you see that I'm gonna need a composition of functions here? I need this to be S. Where that question mark is needs to be arc length, because that's what F2 is expecting, right? F2 is expecting arc length. So I need this to be arc length, but I need this to be arc length in terms of x, so that my rate is in terms of x. So what should I type in there? This, right? So I can put in my arc length as a function of x in here, and it'll be the right thing. So I called it S1. Doesn't matter what I called it, but S1 of a comma x. Does that do it? So notice, in our first work function, this was the force as a function of s, and we needed to transform that force as a function of s into the x variable. Does this do that? We got F2 in terms of x, but it's still a function of s arc length. So what else do I need? So this is still, it's in terms of the variable x, but it's still force as a function of arc length. And I need that rate to be force as a function of x. So yeah. Yeah, so how do I get it to be in terms of x? This is still, so I'm going to need this thing again. Oh, shoot. So there's my rate function for this new scenario. I got to write the force in terms of x, but given that the fact that my force function is defined in terms of arc length, and then I need to transfer that force in terms of arc length into the x variable. Okay, so now I'm going to graph that. Oh, we never set up the work function. But that's easy. Now that I got the rate function, what do I write? W2 of a to x equals integral from a to x this baby right here, t dt. And I'm going to graph it. And how will this work function look compared to the first one? What can you imagine this one will look like compared to the first one? Bigger. What do you mean bigger? That doesn't make sense. The accomplished work will always be bigger. So how will that turn out in the graph? The accomplished work is higher than before? All the y values will be higher up, right? So what will that look like if we did this right? Hopefully we did. We didn't do it right. What's wrong? It should be always be greater, right? It shouldn't be less down here, and it shouldn't be going negative. So we were a little rushed there. Where did I make a mistake? Did I make a mistake? Yeah. Got it right there, and we got our rate function correct. F2. This should always be greater, right? We made a mistake. This should always be up above this because the work accomplished by the ant will always be higher like this. So we'll have to investigate and let you know at the beginning of class next time. Don't forget you got online and written homework right now.
For today's,
Oh, I know.
no,
This needs to be 0. Why isn't it graphing? Where is it? Why isn't it? There it is. Okay, got it to work. One little mistake.